So here we are with the 3-1 assignment for pre-calc. Alright, first thing we're going to do is compute the exact value of the function for the given x value without using a calculator. Ooh, so tricky. Alright, so in number 7 here, we're going to do 3 times 5 to the 0. Hopefully remember that there was a car alarm going off, not mine. Okay, so 3 times 1 from 5 to the 0 is 1, and so that's going to be 3, and yay, we're done with number 7. Okay. Number 8 is going to be 6 times 3 to the negative 2, and hopefully remember that negative 2 means that you're actually 1 over a positive 2 as 3 squared, and so we end up with 6 over 9, or 2/3. Woo. Woohoo, no calculator. Alright. In number 9, we're looking at negative 2 times 3 to the 1/3. So remember that 3 does mean that we have a root of 3. So it actually means that we're going to do negative 2 times the 3rd root of 3, which, as much as you want that to be 1, is not actually 1, so that's the answer. It's really big, sorry. And number 10 is 8 times 4 to the negative 3/2. So, lots of fun here. 8 times 4 to, I didn't give myself enough space there. The 2 is the power of the root. Oh man, even before I go there, I should probably put it in the denominator. So 4 to the positive 3/2. Alright, then we have 8 on top technically, over a square root, whoops, thought I was in a pen, square root of 4, and technically the 4 is being brought to the 3rd, because remember that you can actually write those two different ways. So 4 to the 3/2 can actually equal 4 square rooted to the 3rd, or 4 to the 3rd square rooted. So, clearly I don't really want to do 4 to the 3rd and then square root that, because it's going to be easier to square root a 4 to get a 2, and then take that 2 to the power. But suppose if you wanted to get the square root of 64, that's cool. So, we have 8 over square root of 4 is 2, and 2 cubed. Ooh, so we have 8 over 8, which is 1. Wow, that was a big side step there. Okay. Yay, mental math. Okay, so then the next ones, you need to determine a formula for the exponential function whose values are given. So remember that the idea is that there's an a, b to the x, and a is your starting value, so we're going to want to know what's happening at 0, and then b is your rate. So, taking a look at f of x, that's this first column here, our first number is 3/2, so that means that our a value is going to be 3/2. And then we're trying to look for the rate of how you get from one number to the next. So definitely easier to look at the whole numbers. So how do I get from 6 to 3? I divide by 2, or technically multiply by a half. How do I get from 3 to 3/2? I'm multiplying by a half. So that means that our b value is going to be a half, and then of course to the x. So our official equation for f of x is going to be 3/2 times 1/2 to the x. Alright, then we also have number 12, which is talking about g of x, and g of x has our starting value of 12, so a is going to be 12, and then our b value, again looking from the whole numbers, we're traveling from 36 to 12, which is dividing by 3, or multiplying by a third, and then 12 to 4 is also multiplying by a third, so b is a third, which means that our equation is going to be, for g of x, the a value of 12, and in parentheses a third, and then that being raised to an x. Alright, moving on, we're going to describe how to transform the graph of f into the graph of g and sketch the graphs by hand. Super. So remember that we're looking for what's happening inside by an x or outside. And so in this case, notice that from 3 to the x and 3 to the x plus 4, x has been adding 4. If it was talking about the entire equation plus 4, you'd see a large 4 there. But because it's up there with the x, that means that we're moving it left or right. And in this case, since it's plus 4 and it's up there with the x in Funky Town, we have to do, instead of what you would think to the right a movement, because it's plus, you'd actually move left. So we're going to move left 4 units. And so we're going to graph 3 to the x, and then we're going to move it left 4 and graph 3 to the x plus 4. So we take out our grapher, aka our graphing calculator, or Desmos, but remember that that means that you have mastered the calculator, and so you go to Desmos, but there you go. So 3 to the x ends up, I believe, going through at 1. Alright, let's just go to a table and see. Alright, I have it set up differently. Okay, so 0, 1 is our point right here. It's going through. And then we have 1, 3, and 2, 9. And then, of course, it's exponential, so it's going up, and then also an asymptote at y equals 0. And then to move it left 4, we're going to take each of these points and just move them left 4. So instead of at 0, we're going to negative 4. Instead of at 1, we're going to negative 3. And instead of at 2, we're going to negative 2. Alright, and so now we get this function, which again is very much the same, only shifted left 4. Sweet. Then our next one now has a negative inside of the x, and so a negative in by the x means that we're going to flip it over the, y-axis. I just have to do my little visual for that. Alright, so if we're flipping on the y-axis, and we have 4 to the x, instead of 3 to the x, we're going to go through at 1 again, but of course it's going to climb faster. So we've got that. And then our table has 1, 4, boop, and then 2, 16. Oh, that's not possible. Okay. And so it definitely hops quickly. And then we're going to end up flipping it on the y-axis, and the y-axis is this one right here. And so that means that instead of over 1, it's actually going to be to the left 1, and then at 0. And now it's going to travel up really quickly from here and go down to 0 this way. So it kind of looks like a fancy X. Okay, moving on. The next one is going to be 0.6 to the x, and then 2 times 0.6 to the 3x. So two things are happening there. The 2 ends up stretching it vertically. And then the 3 ends up, and then also because it used to be at 0, 1 for your intercept, you now have 0, 2 as your intercept because of that 2. And then the 3, it's very weird because it's doing kind of the same thing as the other one. It is going to, let's see, what's the stretch, compress horizontally, which actually ends up being the same as stretching vertically. And so it's just really going to get very skinny, tall thing. Alright, so if we go ahead and graph these, let's see. I'm going to graph the original in green. So we graph 0, 1 for our original equation, and over 1 at 0.6, and then a bunch of other small numbers. And then it looks like negative 1, I'm just going to do negative 4, 7-ish. Okay, negative 4, 7. 0.7, oh, which is almost 8. Okay. So this is the original, whoops, wow, that was bad. Alright. This is the original equation, more or less. And again, we are going to change the intercept to be at 2 now because of that 2 that was out front, and then we're also going to stretch it vertically and compress it horizontally, which again just means that it's going to get very tall. It's going to grow exponentially quicker. So if we type in that equation, let's see, 2 times that. Alright, I'm going to plot 0, 2, negative 1. Oh, that's very small. So when we graph here, we've got 0, 2, and then a negative 1, 9-ish. So if we just go back 1 unit, we're already up at 9. And so that's why this one is vertically stretched and then also horizontally compressed, so squished in towards the y-axis. Alright, and then our last one here, we have e to the x, and then 3e to the 2x minus 1. Yikes, okay. So the 3 value is going to end up making this vertically stretch. The 2 value is going to make this horizontally compress. So it's going to kind of add to that stretching as the previous problem did. And then our last one is going to be the negative 1 that's going to shift the intercept down 1. So taking a look at our original e to the x, let's see, e. If you need the e value, it's the division sign if you press second. So I don't want the graph, I actually just want the table. So 0, 1 is our intercept here. And then we have 1 and almost 3. And then 2 and almost and 7 something. So we do have this as our original, and then again we're going to take this and shift it down 1 unit, so I imagine instead of at 0, 1 it'll be at 0, 0. And then each of those points are going to be then shifted down 1, potentially, but then also vertically stretched. So let's go ahead and take a look at how that changes the points. So we're going to, I'm going to type this in. Alright, and so we do shift it down, but then once we shift it down, we stretch it vertically by 2, and so it's actually not at, you can't do one piece at a time, you kind of have to look at it all at the same time. So we are going to intersect at 2, and then, oh gosh, 1 is up at 21, so it's pretty much straight up and down there at the beginning, because the first step over is already at 21. Alright, so that was fun-ish. Okay, let's see if we answered all the questions. Describe how it's going to move and sketch the graph. Okay. So in number 31 here, we're stating whether the function is an exponential growth function or an exponential decay function and describe its end behavior. So remember that the only way that you would know if it's growth or decay is if your b value is between 0 and 1, or if your b value is greater than 1. This is going to be your decay, and this is your growth for the format of ab to the x. So taking a look at our b value here, 3 says that this is going to be growth. 1 over e is like 1 over 2-ish, so that's between 0 and 1. So that's going to be decay. 0.5 to the x is going to be decay as well. And then our 0.75 is also decay. And then I forgot these negatives. So this negative up here actually flips it over the x-axis. So it's going to come from up above and go down to 0. So the growth becomes decay because you're going down towards 0. And then this one here with the exponent of a negative also switches to growth. But we can always just graph, it says. Describe its end behavior. Alright, so I'm going to do number 31 here. And to help ourselves out for the end behavior, I'm just going to type it in and graph it. Oh, I can't really type it in if I've circled all over it. Alright, so 3 to the negative 2x. And so our graph looks like this. It would have looked like this, but because of the negative, it flipped it over the y-axis. And so our end behavior is going to be the limit as x goes to infinity, so to the right of the function, is going to go to 0, and then the limit as x goes to the left of the function is going to be positive infinity because it goes up. Alright, then we have number 32. And in number 32 we have 1 over e, whoops. So 1 over e to the x. Alright, and so our graph looks like this again. And so again, decay because it's going down, downward or decreasing. So we'll do the limit as x goes to infinity or to the right of the function is 0 again, and then the limit as x goes to negative infinity of the function is again positive. And moving on, the next one is 33. Apparently I didn't record that last minute there. So we typed in 0.5 to the x, looks like this, and then I ended up saying it was the same as 31 and 32 because I was just not about to write that twice. And then 34 if you graph. And so if we graph, we end up with this image, which does change our end behavior. So we have the limit as x goes to the right of the function is going to give you a positive infinity, and the limit as x goes to the left or negative infinity is going to be 0. There we go. Alright, and then we get to the logistics equation. So we're going to use a grapher to graph the function, find the y-intercept and the horizontal asymptotes. So, again, not graphing exactly, but we are going to identify those key features. So we type this into our grapher, and you do want to put parentheses as you're doing that in the numerator and the denominator. Alright, and so for this one, I'm going to actually draw it a little bit different. I ended up doing my window so that it was up at 15, so that I could show that at 12 we actually have our horizontal asymptote and at 0. So y equals 12 because it turns out that numerator is the upper bound, and then the lower bound is going to be 0 unless the entire thing has like a +3 or something at the end, because that would mean that it shifted the whole thing up or down. And then the graph itself kind of goes, what's this, 1, 2, 3, 4. So this is going to be at 4, so it comes down in at 4 and goes over. Let's see. To find the y-intercept, we did. That's at 0, 4. Unless it's deceiving me, let's trace and double check. Yep. Alright, and so that is number 41. Sweet. Okay. So then we move on to number 42. And in number 42, you can see that the numerator is 18, so I'm going to probably give myself up to 20. But note that, whoops. We're going to note that at 18 we're going to have our 1 horizontal asymptote, and then again at 0. Alright, and so this one is apparently a very interesting rumor because it is growing very fast. So it intersects at 0, 3, but then pretty much immediately goes up to 18 and immediately down. It's it's more dramatic on the grapher. Okay, and then the next one, again 16, is going to be that vertical asymptote. And then 0 is going to be the other horizontal asymptote. I think I just said vertical, but I meant horizontal. And so we graph. So this one goes through at, I believe, 3. So again, type in a 0 and press enter. Up it's at 4, so 0, 4. It's a comma. And just like the previous one, it jumps pretty quick up to that 16. And then the last one of 44. If we type it into our calculator, we're going to want it to have a window up to about 10, because we need to have the horizontal asymptote at 9, and then at 0. Okay, and so we'll type it in. And so intersecting at 0, 3, we have this curve like that. Alright, so again, you don't really need necessarily the grapher to find the horizontal asymptote, because it's going to be up here and then always at 0. And then the intercept, you can of course just plug in a 0 for the x and see what your y is. Alright, and then we have our last one, which I did work out on the answer key, so if you pop over to that, you can also see some work as well from previous moments. But in number 51, we are using the data in table 3.7 and assuming the growth is exponential. When would the population of Austin surpass 800,000 people? So we've got two pieces of information. We've got our x values and our y values. And so we're going to use those two pieces to figure out what our initial population is, and then also what our rate is going to be. So as you can see, at least to get from this number to this number in our growth, we end up, let's see, what's 711,000? Because who doesn't know? 711,265 divided by 656,562. Alright, so if we multiply these two numbers, our rate, or divide them, our rate is 1.08, a bunch of other numbers, 3. And so that's going to be our growth rate. And then our intercept, sorry, wait, that was assuming that there was a change of 1. Okay, so let's do it the other way. The idea is that we have y equals ab to the x. And we actually have an x and a y, right? And we have kind of what we're going to call our 0 year. Oh, I'm doing that the wrong way. Our 0 year at 1990, and then our year 10. So these are our x values. Don't know why that's not working. There we go. My pen turned off. And so now we're going to say that to get from, for Austin, for instance, or which one? Yeah, Austin. Our 0 point is at 465,622. And then at 10, we're at 656,562. I was reading the table wrong before. That means that our initial is going to be 465,622 for the A value. Our B value we don't know yet. We'll find that in a second. And then our X is going to be 10, because we do have to talk about how it's growing over 10 years and not 1. And then at 10, it's going to be that other number, 656,562. And so we can work backwards in order to solve for B. So for instance, we can take 465,622 and divide it to both sides. And so that division leaves us with 1.401 as b to the 10th. And there's a few ways that we can do this, but maybe you remember back to our exponentials. And so if this is written in exponential form, we can also write it in logarithmic form. Oh, but that's if the variable is it. So instead, we can just square root, or 10th root, excuse me, this number. And so how do you do 10th root? You type in 10 go to your math, pick number 5, because that's the whatever root you want. Do it of the answer that you had before, and so we end up with a b of 1.03. How many decimals do I want? A lot. 50. So that means that for number 51, our equation is going to be y equals 465,622, and then times b, which we just got, 1.0350 to the x. And so now they want you to figure out when we're going to surpass 800,000. So that means that we're putting 800,000 in for y, and we'll solve backwards. You can, of course, do some guessing and checking if you don't feel like doing logs, which probably no one does. But, of course, I will show you how to do it backwards. So 465,622 should be divided to both sides, which leaves you with 1.7181, and that's going to equal 1.03, that's a 350, to the x. And so if we rewrite this in logarithmic format, we can say that it's log base 1.0350 of x, of 1.07181, and that's going to equal our x. So if you have a standard calculator, you're going to be able to just do this in your math and scroll down, but I don't, so I'm going to have to do log base 10 of 1.7181 divided by log base 10, it's a change of base, of 1.0350. Either way, that's going to equal our x, and our x is in years. So when we get an x of 15.73 blah blah blah, we can add that to the starting year of 1990, and we're going to say that apparently in 2005, that's when the population reached 800,000, because clearly that's in the past. Alright, so the next one here says, using the data in the table, assuming the growth is exponential, when would the population of Columbus? So now we get to do the same thing, making that formula for now Columbus instead of Austin. So we'll use these pieces from the table where y is going to be 711,000, a is that other population of 632,000, and then x is going to be 10, and we'll plug it in. Once you plug it in, we'll divide both sides by that 632,000. Which results in 1.1238, and then we'll 10th root that, which results in a b value of 1.0117, and so your official equation is going to be y equals 632,910 times 1.0117, that should be a 7, to the x, and that is what you'll use in order to solve for when this equals 800,000. Doing the same process as before, we'll divide by that 600,000, which results in 1.2640. And then we're solving to get that x value, so a few ways to do that, but you can rewrite it as log base 1.0117 of 1.2640, and that's going to equal x. And so our years are 20.14, but plus the 1990 from where we started, means that in 2010, apparently, was when that happened. That's population surpassed 800,000. So the next one in number 53, we want to assume the growth is exponential. When would the populations equal? So we got to set our two equations equal to solve for x. Looks like we're going to run out of time on this video, so I'm going to do 53 and 54 on another one.